All generic services defined by the fiber channel are assigned a fixed address, referred to as their well-known address. If a service is present, it will reside at that well-known address. If a service is not present, its well-known address is unused. Common terminology often used name server rather than directory server. This is the same service located at FFFFFC. The three most common well-known addresses are: FFFFFE is the address for Fabric F_port service. FFFFFD is the address for Fabric Controller service. FFFFFC is the address for Directory server, often called the name server. Less common well-known addresses include: FFFFFF is for Broadcast. FA is for Management server. FFFFFB is for Time server. FFFFF8 is for Alias server. FFFFF7 is for Key server. FFFBXX is for Multicast. FFFCXX is for the Brocade domain controller, embedded port/switch ID. A link initialization occurs to determine what port type we are dealing with when a cable is plugged into the SAN. Ports within a SAN mainly fall into one of four types. Generic port, G_port on a switch that detects the attached port type and auto-configures to match that port type. Expansion port, E_port on a switch that allows connectivity, expansion, to another switch. Fabric port, F_port on a switch that provides access to Fabric services. F ports connect to N ports to form a Fabric point-to-point. Node port, N_port transmits and receives fiber channel data frames in a switched Fabric environment. N_ports represent endpoints in the Fabric, such as SCSI initiators and SCSI targets. Traditional N_port initialization works as follows: the N_port sends FLOGI to Fabric server, FFFFFE, to obtain a valid address. Next, the Fabric server responds with an accept, containing the assigned address. Next, the N_port sends FLOGI to the name server, FFFFFC, to start the registration process. HBA ports will query the name server to see if there are any SCSI targets logged in. The N_port also sends SCR to the Fabric controller, FFFFFD, to register for state change notifications, RSCNs. Once the physical link is established, the node sends a FLOGI frame to the port to allow it to communicate with the rest of the Fabric through the Fabric login. This frame is received by the login server. The switch then sends an ACC reply that contains the N port address, FCID, in the destination ID field. Next, each node performs a name server registration. The name server obtains information from the node through the port login frame and through subsequent registration frames. Information in the name server is stored in the form of database objects. The node may register values for all or some database objects depending on the requirement. The most commonly registered objects are Fabric address, WWPN, WWNN, and ULPs, classes of service supported, and port type. The node also requests a list of nodes that support the same FC4 upper layer protocols as itself. This list usually depends on whether there are restrictions placed on which devices the node can talk to through zoning. Each N_port must be assigned a 24-bit address, FCID. With a switched Fabric, it is the switch itself that automatically assigns an address to the N_port. The switch will assign an FCID that is unique in the Fabric. This address is assigned when the N_port logs into the Fabric. The address is specified as 6 hexadecimal digits and is divided into 3 fields: domain_ID, area_ID, and port_ID. Each switch is assigned a unique domain_ID between 1 and 239. It is the switch domain_ID that becomes the first byte of the address for every N_port attached to that switch. Now this is where it gets interesting, because the TLL standard allows some leeway in how the last 2 bytes in the addresses are assigned. The 2 major switch vendors, Brocade and Cisco, each have a different way of allocating these last 2 bytes. Brocade puts the port number that the N_port is attached to in the second byte, or area_ID field, and leaves the third byte as 0, unless they have to steal some bits for port numbers above 256, or if there are multiple logins from the same port such as an AG switch. Cisco will leave the area_ID field as 0 and assign the third byte as a sequential number beginning with 00, on a first-come, first-served basis, as port's login. There is a persistent address table that is kept to ensure that if a port logs out, and then logs back in, it will receive the same address. The details of address allocations are much more complex than we've just described here, and are beyond the scope of this course. But you should remember two things. First, when connecting a device to a switch, the device will receive its fiber channel address from that switch. Second, one of the reasons that there are incompatibilities between Brocade and Cisco switches is because they handle address assignment differently. This is why you will normally find that a data center has all Brocade fiber channel switches, or all Cisco fiber channel switches. They are usually not both found in the same data center. After receiving an FCID, each N_port will log into the name server with a PLOGI, port login. Once logged into the name server, the port will send several fiber channel services frames to register specific information with the name server. These frames will specify which fiber channel classes of service are supported by the HBA, the FC4 protocols supported, and its mode of operation, N_port. HBAs from different vendors, and storage device ports, may register additional information such as WWNs and symbolic node names that include text that describes the manufacturer, firmware version, and other information. Once the HBA has sent all the frames with information it wants registered with the name server, it then begins a series of queries. This step allows the HBA to find out what storage targets are registered with the name server. Each query is sent with a fiber channel services frame and responded to with an accept frame. The first query asks the name server for a list of FCIDs that have registered as SCSI FCP devices. Once it gets this list of FCIDs, the HBA will ask the name server for relevant information about each registered FCID. For example, it will get port WWNs associated with each FCID. This is where zoning is important. The name server will only return information about registered devices that are in the same zone as the HBA port. So if there are 10 storage array ports registered in the fabric, but only one of them is in the same zone as the HBA port, the HBA will only learn about that one storage device. When the HBA is done asking the name server for information, it will log out of the name server. The node then attempts a PLOGI to all nodes from the list it receives from the switch's name server. It provides a specific set of operating characteristics associated with the destination N_port, such as which classes of service are supported. It also initializes the destination end-to-end credit. The process is repeated as other nodes are attached to other ports on the switch. Once the HBA port has logged into the storage array port at a fiber channel level, it must then log in at a SCSI process level. Since the HBA wants to exchange SCSI data over fiber channel, it must perform a process login by sending a PRUI, process login, extended link services frame to the storage array port. The storage array port responds with an accept frame. Information carried in these frames specifies which port is the SCSI initiator and which port is the SCSI target, and whether to use SCSI XFER_RDY on read operations. Usually XFER_RDY is used only for writes.